Design of low-noise amplifier for wave applications. Abstract. This paper proposes a transformer-based low-noise amplifier in 45 nanometers CMOS process and working at E-band frequency range. The CS amplifier is used because of better noise performance, and the cascade stage is used for higher gain. The impedance matching network is used to obtain 50 ohms. This LNA gives a gain of 11 dB at a frequency 67 GHz and noise figure of 43 dB at 67 GHz frequency. Index term CMOS process, CS amplifier, LNA, noise figure. Introduction. The E-band range, 71 to 76 and 81 to 86 GHz, of frequency has become extremely important with the advancements in the 5G communications too. The data rates can be increased to a good number if the communication takes place at this range. This can eliminate the cost of optic fibers, which are usually used for high-speed communication too. LNA, low-noise amplifiers, play an important role in the wireless receiver system, and its gain variable is of very high importance at a high frequency 1-2. There have been some research on E-band LNA at 90 nm 1-2. This paper proposes a LNA at 45 nanometers technology, which will help in reducing the area and also increases the speed, which better fits the receivers used in the new generation 5G phones. 2. Circuit design. In this high-frequency low-noise amplifier design, cascade topology and common source topology are used. Although the cascade topology, the stack structure, provides higher gain but requires a high drive voltage. The common source stage is used as it has a better noise performance, and also it consumes a very less DC power, which is suitable for low power application 4. Hence a combination of both is used so that there is an equal trade-off between the power and the gain. Figure 1 shows the implemented high-frequency 3-stage low-noise amplifier. The inductor values are chosen such that they match the input impedance of the transistors for next stage 1. The capacitors are used for eliminating the DC components, if any, and provide good waveform at the output. The last stage consists of a common source stage that amplifies the power of the signal transmitted. Fig 1. Schematic diagram. 3 circuit specifications. The transistors NM0, NM2, and NM4 have larger width than usual in order to provide adequate current to drive the next stage. Whereas NM1 and NM3 have usual 120 nanometers width to provide less resistance in the path. It is worth noting that their less resistance is required because they act as input resistance to a common gate amplifier. The stack structure behaves as a common gate amplifier. The table I list the dimensions of the transistors and library used to simulate them. The resistor, R, capacitor, C, inductor values have been determined for proper matching and biasing. The table 2 lists the values used. 4. Simulation results and analysis. Above schematic has been designed in the Virtuoso tool using Schematic Editor XL. The analysis that have been performed are as follows. Transient. The transient analysis has been performed for 200 ps with a -20 dBm source as input at 67 GHz frequency, which is the starting frequency of E-band. S-parameter analysis have been performed for frequency ranging from 67 GHz to 90 GHz with port 0 as input port and port 3 as output port. NF, noise figure plot has been obtained by using the direct plot options in the 8L window. The direct plot option contains various results that can be plotted from the various analysis performed. VSWR, voltage standing wave ratio, VSWR plot has been plotted from the direct plot option present in the results option of the 8L window. The gain obtained is 10.96 dB, Fig. 2, and the noise figure ranges from 43.1 dB to 43.5 dB, Fig. 4, in the spectrum of 67 GHz to 90 GHz frequency range. The S parameters are used to analyze any high-frequency circuit. They provide us a method to characterize any high-frequency circuit. The very low value of S11, Fig. 3, suggests that there are very few reflections, which is very much necessary for the RF circuits. The reflections, if there are any, in any RF circuits can cause the circuit to misbehave and increase the power loss. VSWR provides information about the standing waves arising due to reflection of electromagnetic waves from the metal contacts. VSWR values ideally should be 1, and in the current design it has a value of 1.0108. The Vswr plot, Fig 5, is as shown below. The results are tabulated and is shown in the following table. 3. V conclusion. The LNA has been designed and simulated using Virtuoso and Spectre tool of Cadence Design System respectively. The complete design is done using 45 nanometers technology library and the analog lib file for the resistors, capacitors, and inductors. The gain is around 11 dB and can be further improved by correct. Acknowledgement. This work has been supported by the professors of Electronics and Communication Department of RV College of Engineering, Bengaluru, and would like to thank the department for providing the necessary software and the guidelines for the completion of the work.